Get the hell out of that place. Oh, it's beautiful over here. Yeah, until it explodes.
Well, yeah, I guess.
Then he says, well, you live by Yellowstone.
I guess we'll be getting some thermal energy from somewhere eventually. But okay, so here we are. It's week 4. We're doing Stirling engine theory, and also I just wanted to give you all a heads up. The course website needs some. Well, it just needs a little bit of updating. I've constantly been tweaking this thing as we've evolved. When the course first started, there was some solar, electric, and wind, which on the one hand makes sense because they both are typically making electricity. But we didn't really have a good solar thermal course, so I figured 243 in the spring would just focus on solar electric, and here we're doing solar thermal and wind. But anyway, so I will continue to update this. The reason this looks the way it does is because the last time I taught it, we didn't teach it in 2015, but in 2014 we were taking down the old wind turbine. Yeah, and I don't think the video's there anymore, but I was showing here. Here's what we did for the course. We were dismantling the old wind turbine. So, the plan is, just on that note, to go and help Kettle House get ready to install the wind turbine that came out of the Hellgate Canyon. So, okay. Well, I want to get back and do a little bit more theory on just wind turbine theory. So let's just go through. Let's go through these notes. Give me one quick second. I just had him a second ago. Let me pause it. Okay, so we've seen a couple videos on how the 3 different types of Stirling engines work, and I just want to get into some of the physics a little here. So I'm going to dig up some notes that I made a few years ago, and so I'll just kind of go through these equations. So yeah, and I'm going to look at this, but then I'm going to rederive it on a separate sheet so you can kind of follow along as we go. So the Stirling engine, rather than being chemical, if you note there's no combustion going on there, it's not a chemical energy reaction, it's just mechanical. So the ideal gas law works like so. So you have PV equals nRT, and let's just dig into that a little bit. One thing that really needs to be made very clear. At first the equation, you're like, why do I have these 5 variables in the equation? And R is called the gas constant, and this is what's kind of neat about it. It's the product of the Boltzmann constant and the Avogadro constant. So let's just look at each one of those, and we'll sort of figure out what that is. It is a fundamental constant in a lot of ways. I mean, I think by now we understand what pressure is, we understand what volume is. And it's just, this is just, can you count the number of moles or the number of atoms or molecules? Because, all matter is quantized. And then this is the absolute temperature. But let's just look at the ideal, the gas constant for a second. And we'll see right away that it can be placed in all different kinds of units. So there's some alphabet soup for you, but this is the most common one. We know what a joule is. A 1 degree Kelvin is the same as 1 degree Celsius. at least the changes. The scales, of course, are different. This is the absolute temperature from absolute zero, and the moles are just how many moles of substance. And it could be different. You might have moles of oxygen combined with moles of nitrogen. Nevertheless, it's just the total number of moles of working substance. So there's the common value, and that's the one we can look at. But you can see you could also measure it in calories instead of joules. You could measure it in cubic centimeters times kilopascals. You can measure it in liters times torr, etc. But this is the most standard one. And so let's break it down just a little bit more. So the units on R, it's just energy, and that was your joules, per temperature times moles. And if you remember, 1 mole equals 6.023 times 10 to the 23rd.
Mm-hmm.
Yeah. Yeah. So it's a large number, and it's just a number. It's like 10. It just happens to be really large, or 100. It's a mole. That's all it is, a number. Okay. So the first thing to note here, and if we just get R by itself, let's just do a little bit of algebra and say, here's R equals, we'll keep PV in the numerator and put NT in the denominator. So the very first thing that pops out is you look at this thing, you're like, oh, look, P times V is energy. Pressure times volume is energy. And then let's break it down one more step. So we know that pressure, typically you think of that as force per unit area, right? Because when I say, what's the pressure in your tires? Well, it's PSI, pounds per square inch, and pounds is force, and square inches is area, or newtons, which is, pascals, which is newtons per square meter. Yeah, pascals is another one. So, but if we do something kind of tricky, we can say if we multiply force times a length, and we multiply area times a length, it doesn't really matter what length we're talking about, force times length equals energy. It's that simple. So remember energy Y101, and the same thing, area times length equals volume. So pressure is nothing more than energy per unit volume. So if we multiply, make sure that's looking more like a P and not like a rho. So pressure times volume equals energy. Because you can kind of might think of pressure as like specific energy, you know, how much energy is in a given volume, and then multiply it by the volume, and that's how much you have. So another way to think about this, or another thing that's just worth noting, is that pressure is intensive, variable, and volume is extensive. And here's what I mean by that. So if I have a box of air at some pressure, the pressure is the same throughout the entire box. Yeah. It's in a static. The neat thing about the Stirling engine is that the pressure is kind of always changing, and it's changing because the temperature is always changing. But in general, unless there's motion, the pressure is just the same everywhere. Okay, so that's how the ideal gas law is, sort of key to understanding Stirling engine. Okay, so P is pressure, V is volume, N is the number of molecules or moles, R is a constant, T is a temperature, and then I just did the same little thing. So pressure is force by area, multiplied by length, that's energy per volume. Volume is length cubed, multiplies together, and energy sort of pops out. And what we're doing here, we're going from, again, the Stirling engine, it is a thermal engine, and we're going from the ideal gas law so we're going from thermal energy into kinetic energy. That's the whole point. The whole point is to get that flywheel to spin. Why do you want the flywheel to spin? Well, you want to drill a hole in something or run a conveyor belt or what have you. That's where that's the whole point. Not the most practical for transportation, more for stationary devices, where a flywheel is not a big
Could you
penalty.
use one to maybe power a generator if it was large enough?
Oh, absolutely, yeah. If you wanted to make electricity, yeah, spin a magnet and make electricity, absolutely, sure, absolutely. Sure could. Okay, now I want to look a little bit into rotational kinetic energy. We've spent a lot of time, talking about linear energy and potential energy. Up until now, in the energy tech set of courses, we haven't really spent much time at all defining rotational kinetic energy. So that's what I'd really like to do next, because it's important. If you look at your wind turbine blades, look at your flywheel, look at really anything that's spinning, I'd like you to be able to define how much rotational energy the thing has. Okay, so let's do that. And I've got these notes to go by, but let's just start from scratch again. That's a fun slide, isn't it? So rotational kinetic, because it's moving. I mean, it's not going anywhere fast, but it's moving. Energy. And this looks a lot like linear kinetic energy, but it's different. But it's still E equals 1/2 I omega squared. Now let's do a little bit of dimensional analysis. We know that the dimensions of energy equal mass times length squared over time squared. Okay. Now we've seen this before. This is angular velocity. It's measured in RPMs or hertz, or in hertz, or another way to think of hertz is radians per second. Okay, so the dimensions of omega equal 1 over time. So what I'm trying to do is sort of get to what the dimensions of this I thing might be. So on the left-hand side, we've got mass, length squared over time squared. And on the right, we have something times 1 over time squared. So obviously, knowing this, the dimensions of I must be mass times length squared. Okay, so let's do a little investigation into what I might be. So there's two different things. You can have either angular momentum or angular energy. So this thing I is just called the moment of inertia. And I remember, gosh, back back very first days teaching this course, someone said, well, inertia is conserved. And I said, well, it is, but inertia, inertia itself doesn't have units. There's not like an inertia unit. It's just something we sort of talk about in language. And what people usually mean is like it's momentum, like how it's moving. It's, think back to Newton's first law, objects in motion tend to stay in motion. Same thing, objects that are spinning tend to stay spinning. So, and the word moment, maybe the easiest way to think about it is like torque. And sometimes if you've got something and you want it to spin, you put a torque on it, and that's just also called a moment. You're putting a moment on it, which it's just kind of old language, but and so it's weird, but that's just what it's called, moment of inertia.
Okay.
Yeah. So let's look and see what the moment of inertia is for several things, different things. Now, we don't really have to worry about this integral. It just means if we just got some weird blob shape and it's spinning, that integral sign just means we sum up all the particles. It's just a fancy way of saying we don't know where they are, but we're gonna sum them all up. What we really need to do here is just go down and look up a few values, because in general, all the nice math is. Another thing that is maybe worth mentioning is the moment of inertia. All of these values we're looking at here are actually vectors, and the reason for that is that I could have this thing spinning about this axis, kind of like spinning like a top. I could also have it spinning this direction, or I could also have it spinning this direction. So depending on how something's spinning through space, you would have three separate moments of inertia. But in general, you're not going to make some random weird shaped flywheel. You're going to make a flywheel that looks like a flywheel. And so that's what I'm trying to get to. This is kind of just, all of the physics combined. But if we come down here, there's a nice set of tables, at least there used to be. Let's see. List of moments of inertia. There we go. So if we kind of come down here. So the simplest one, and this is something that really isn't of all that much use unless you're talking about a planet flying around the sun. The simplest way to look at it is the moment of inertia of a point traveling in a circle about something else is just I equals the mass times the radius squared. And so that should go back and say, okay, there it is, mass times the radius squared. And now we know so it's a different animal. It's a different way of combining mass and length, but the dimensions work out just right, just perfectly. Okay, we won't look at these rods. So here's the one that's relevant to what we're doing. And so as I mentioned, there are three separate moments of inertia. If this disk, this could be a flywheel, just a solid flywheel, maybe it's got one little hole in the middle, but solid flywheel, equals mr squared over 2. And that means it's spinning about the z-axis. So just imagine a pizza pie. You're going to spin that about the z-axis, and that's the value. So let's go back here. Mr squared over 2. Now, if you look at that, you're like, gosh, why would this be less? Why would a disk? Because you might think, well, gosh, the disk has more mass, right? It's just there's more of it. But some of the mass is here near the center, meaning there's less inertia. Think about the ice skater who's got her arms out to the side, and as soon as she pulls them in, she spins faster. She's made her moment of inertia less. She spins faster because her energy is the same. The energy had to go somewhere. Instead of just all this stuff out here at the sides, she pulls them in and then spins faster. So that's that deal. And it's even less if you're spinning it about this axis or this one. So that's more, I don't have anything circular, but that's more if it's spinning this way instead of this way. I mean, you wouldn't take your flywheel and turn it on its side and spin it that way. You know, what's the point? Because it would have less, less moment of inertia. So that's why if you spin it that direction, it's half again. So that's just explaining those two numbers. Okay, so now we can go back and look at this guy. So there again, I've just shown that the dimensions of angular velocity are 1 over time. The dimensions of the moment of inertia are mass times length squared. Now, what I've tried to show here, I've tried to show a ring. I don't know how good a job I did there. Let's just go back down. There's probably a better one here. Okay, there it is. So here's a ring. And really, if you remember back to those videos with the Stirling engines, each one of those was some kind of donut. So it's a ring. And so what you do is take the average of the outer radius and the inner radius. So R2 is from the center to the outside. R1 is from the center to the inside. So that's what I'm attempting to depict here. That's what I'm attempting to depict here in my note. There's an R1 that's right there and an R2 that's out there. Let me just draw that. Just draw that again for you here. So we'll draw a side view of our flywheel. You know, it's going to have some spokes, but we'll kind of ignore those because the majority of the flywheel is sort of out here, and it's got some thickness to it. My best sort of 3D rendering, and obviously it's spinning here. So, so to get to here, this is R2, and to get to here, that's R1. So I equals 1/2 m R2 squared plus R1 squared. Okay, so that's the moment of inertia. I equals 1/2 mass. And what's the mass? Well, you just take the whole thing and stick it on a scale. That's how much it weighs. Just how much, what its mass is. And another way of thinking about it, it's sort of like, it's kind of like the average of the two. So if you took the outside and squished it in, and you took the inside and squished it out, you'd come to the average, and all that mass would be back where that one little point was. You'd kind of be back at the starting point. Okay, so hopefully all that pulls together in one little deal. So let's look. What I want to do is, let's just say we've got a flywheel, and it's got an inner radius of 5 inches. We'll convert that to meters. It's got an outer radius of 6 inches. We'll convert that to meters as well. And I'm going to say that thing is spinning at 3,000 RPMs, revolutions per minute. And I'm going to convert that into radians per second. So I'll go ahead and write this again. So I've got forgive me, big R equals little r, whatever, R1 equals R1 equals 5 inches. R2 equals 6 inches. Kind of lazy, I know, but too bad. There it is. No difference between the two R's. And then we're running at 3,000 RPMs. So omega equals 3,000 RPM. And the question is, what does I equal? Right, because we have everything we need. Well, sorry, what does, what we're really looking for is what does, Well, no, we need to know that. Equals what? And we also need to know what the energy equals. Okay, and I think somewhere in here, we say what the mass is. Oh yeah, I just say the mass is 1 kilogram. 1 kilogram, so 2.2 pounds. So this is a little flywheel. Might be something like you'd see in the Segways. I don't know if you've ever seen those Segways that Dean came in, those little two-wheeled scooters that sort of balance and people are teetering around them. Sometimes you see the security officer driving around in the airport or whatever, the people trucking around on vacation or whatever. But there are a lot of little flywheels in those in those Segways, and they're used for balance, for steering. Okay, so I think I've got a little, yeah, so here's what I did. I didn't put all the conversions in, but so to find the moment, I put in the mass to be 1 kilogram. I put in the radius to be 0.128 meters. 5 inches, that's the same as 5 inches exactly. I think I did those, I must have done those numbers offline. But 5 inches is a little over 1/10 of a meter, and 6 inches is 154 thousandths of a meter. And then from there, you can see, all I did, I multiplied the mass times the radius squared times the other radius squared. I think what I might do is Mr. Grins. Let's do it this way. Let's put in some inches just for fun. And we'll do it in LBS. And we'll just take all of these guys. And we'll change this to inches. This is going to equal that times, let's just check my memory here, 39.1. 39.1. Yeah, that's about right on. That's if I just take that and put it in number format and just keep it to 2 decimals, that works. I can actually just take this guy and drag it over there. 6.02. Okay, I was pretty close. Might be something like 39.09. Drag that over again. I don't remember exactly what the conversion is from inches to meter. Let's just go look it up really quick. Let's go meters to inches. 39.37 it's saying. Okay, let's try that out. 39.37. Okay, well I must have had some rounding errors there. Anyway, you get the point. Equals this times 2.2, and then so we could do this again in pound. And remember back when we were talking about the ideal gas law constant, the gas constant. You can put in all the different, the number is going to come out differently depending on what units you are, and the same thing obviously is true of moment of inertia. So pound inches squared. And if we just Control C, Control V, it's just larger. Just because there's more inches than there are meters. Not a big surprise there. Okay, so that's that. And then finally, the other thing we want to find out is the energy. I mean, the whole point is like how much energy does this thing have? So I was just over, just as a side note, I was just over at Free Cycles here in town, and they would really like to be a more sustainable operation. That's possible. I think it is. I mean, it's always possible. And the one thing that Bob was talking about would be to have some human-powered gizmos over there. And so I'm like, it sounds pretty good, but one human power is not much. It's like 100 watts, maybe 200 or 300 watts on a good day for any length of time. But you can imagine, maybe you've seen the pub bicycle that pedals around town. Next time you're downtown on like a Thursday or Friday night, you might see these people. There's 8 people on a bicycle. They're driving around and maybe drinking beer or whatever. But if you had several people pedaling a larger flywheel, then you're talking. But so then the question is, what can I actually run with that flywheel? So that's the whole point. Like, how much energy is there in that flywheel? Because it's gonna ramp up and ramp down. And believe it or not, some of these high-end data centers, computer data centers, actually have a flywheel sitting there spinning. It might seem kind of weird and old, but if the grid goes down and your batteries wig out or whatever, you still that silly flywheel spinning around on the corner. It keeps that keeps it rolling. Okay, and another way, and one more thing on that. Another way to think about the flywheel is that it's analogous to a capacitor. So think about your battery. If you're going to charge up a battery, you can't charge your battery just boom, right? You stick your phone on charge. It takes a while. The electrons to flow through there and find the little spaces. A capacitor, on the other hand, can take a charge in a big hurry. Flywheel is the same way. It can speed up or slow down in a big hurry. Just watch the RPM gauge on your engine sometimes. So that's the advantage. So a flywheel is a lot like a mechanical capacitor. So that's how I like to think about it. Okay, so the last thing the goal of this exercise is to see how much energy is in the flywheel. So if it's spinning at 3,000 RPMs, I've got to convert RPMs to radians per second. And how do we do that? How do we convert from RPMs to radians per second? So here's your 3,000 RPMs. In every minute, so I've got minutes in the denominator here, minutes in the numerator here. In every minute, there are 60 seconds. And now I've got to get rid of these revolutions. So I'm going to put revolutions in the denominator, and I'm going to put 2 pi in the numerator, because just look at this circle for a second. 1 revolution is the same as 2 pi radians. That's how big of an angle you went through. And that's, my little scribble is hard to read there, but I think it says 314. So yeah, so here it is in Microsoft Excel, going from 3,000, you go to whatever value there is in B16, which is 3,000 times 2 pi divided by 60. So I just did that same math, and there you are with 314. Okay, then finally, we get the total rotational energy of the flywheel. And it's going to be in joules. That's another thing, like what, 1979 what? Well, it's joules, because joules are in kilogram meters squared per second squared, because that's exactly what we had. We had the mass was 1 kilogram, we converted into meters squared, and then of course the units, and again, sorry that's hard to read, but it says 314 seconds to the minus 1, so 314 radians per second. Okay, so there it is. And what's that? It's 2 kilojoules, not a whole heck of a lot. You could imagine spinning a little flywheel like that up on your own in just a few seconds. But if we go back, I just want to go, you guys see all that? Is it
Can you
clear?
go back to
To the notes? Yeah.
part?
This one right here?
Yeah.
Yeah.
There we go.
Yeah, yeah. So all I did, I kind of wrote the whole thing out. There's 1/2 times 1 kilogram, 0.128 meters squared, plus 0.154 meters squared, gives us 0.0401 kilogram meters squared. Stick that right in there for I. There's the I right there. There's the 1/2, and that's our omega squared. Gives us 1,979 joules. Joules. Yeah. Okay. These I was just showing in this slide the four strokes. They were shown in the video. These are the 4 strokes of the Stirling engine at so one stroke as the gas is heating, the pressure goes up. This just says isothermal expansion. So as that piston is moving, the temperature isn't really changing much. And then at the other end of it, when the piston is moving the other direction, the pressure goes down. And then as the volume is changing, so in this case, the piston is moving away, the volume is expanding. In this way, the piston is going the other direction. So the cycle, the thermal cycle, the pressure volume cycle. You can also imagine doing like a pressure volume temperature cycle, which would actually be a 3-dimensional graph, which would be kind of fun to try to draw, but or not.
No, you see it.
Yeah, well, so this is what's happening inside the what I've drawn here is just a beta style. Yeah, so this is sort of I've numbered this. So number 1 is just showing that the volume is going up. At number 2, the volume is really not changing. Right at that, as that piston reaches the end, the pressure goes down, sucks the thing back the other way. There's a little velocity here. There's a little bit of friction there. Number 3, the thing is the volume is getting less, and I'm talking about this half of the chamber where the heat is. That's what that little fire is. The squiggly M, that's a fire, and then number 4, when that fire is heating, the pressure is going up. So is the temperature, and then the cycle continues. So there's kind of a stop motion of what's going on inside that Stirling engine. Okay. So one thing we could do here, I said to find the power rating inside your engine, so we know that because obviously a bigger engine with bigger pressure, it's going to have more power. So I said let's go, and so power is the change in energy over the change in time. So what you're looking for is the change in pressure and the change in volume as a function of time. And you can see on this little diagram, well, the pressure, the volume is changing here, the pressure is changing here, then the volume changes again, and the pressure. If you sort of like add each one of those changes up, you'll see how much power there is. And if you sort of clock it, how long did it take to go around that cycle? see how powerful it is. That's the power. So we kind of, what I try to do here is sort of go from energy. So remember, we spent a little bit of time discussing the ideal gas law. We remember that pressure times volume is energy. And in order to get the power, we just need to know that change. So I'm just going to kind of like throw that out there as something to think about. Maybe we'll do a problem later where I give you some numbers to work on, but that's something to work on, just to chew on a little bit. Okay, I think I got one more slide. So we've done the Stirling engine lecture. We went through this little spreadsheet. Got this one last bit. Let me see what else we got here. I don't want to get too crazy. I'm going to take a little break here, and then we'll dig into this one last time, and then we'll be done for the day. Went for 40 minutes. It's a little longer than usual, but that's okay.